So here are the solutions for the practice quiz that you guys got today. Um, so we're going to have a simple machine in this first case. We're trying to get a piano from the stage to the top of the amphitheater. So we're going to go like this. We need to go 3.5 meters up in the air. And we have a 12.5 meter long ramp to do it. And the thing we have to move right here is 580 kilograms. It's the piano. When we get to the top. So part A asks about the IMA, or the ideal mechanical advantage. And again, that's purely based on the distances. It's based on how much of a benefit we're getting by going 12.5 meters versus 3.5 meters straight up in the air. So that is going to be the D in over the D out. And again, the input is the side that we actually worked on. So that's the 12.5 meter side. And the output is the fact that we got 3.5 meters up in the air. So if we work that out, 12.5 divided by 3.5, we end up with a ideal benefit of 3.57. So ideally we should get a little over 3.5 times the amount of force out of our machine than we put into it. So ideally is what B is about. How much force do you have to expend to move the piano? Ideally would be your F in. And since we're talking about the ideal situation, F in, finned in equals fouled out. So the work we put in is equal to the work that we get out of our simple machine, or F in times the 12.5 meters should equal the weight of the object, 5,800 newtons. Remember, because what we really get out of this is we raising the object up in the air times that distance of 3.50 meters. So if we solve that, we have 5,800 times 3.5 divided by 12.5, and we get an ideal input force of 1,624.20 newtons with 3 sig figs. So that means ideally to move this 580 kilogram piano up this ramp, we would need 1,620 newtons. In C, it says it required 4 people who each exerted 500 newtons of force on the piano. What was the AMA of the board? Again, AMA is the actual mechanical advantage. So that's a ratio of how efficient was our machine. We know it's not perfectly efficient because it would have only taken 1,620 newtons to get it up the ramp. But in reality, it's going to take 4 times 500. So we have 4 times 500, which is 2,000 newtons, is the real force to push it up the ramp. So AMA, again, is the output force. What do we get out of it? Divided by how much we put into it. So in this case, what we got out of it is we lifted a 5,800 Newton object, but it took us 2,000 newtons to do it. So if we work that out, 100 divided by 2,000, we get a real benefit to our machine of 2.90. So we were hoping for a benefit of 3.57. We only got a benefit of 2.90. We know they weren't perfectly efficient because it took us 2,000 newtons, and ideally it should have only taken us 1,620. So the last part is asking about what is the efficiency of the board. So D is efficiency, and efficiency is just the ratio, the AMA over the IMA. How good did your machine do divided by what would have been perfect. So we have 2.90 over 3.57. If we do 2.9 divided by 3.57, we get an efficiency of 81.2%. So that would mean that 18.8% of the energy was lost due to friction, more than likely. So there's the first problem. Hopefully all of that makes sense. Again, remember, input is this side here. What do we actually do? Out is this, which is the far side, which is if we would have had to lift the object ourselves without the benefit of using the ramp to do it. So the next slide, the next problem talked about a 335 kilogram boulder. So here's our boulder. It fell on top of your homework, so there's your homework strapped down there. So what you did is you found a pole that is 1.95 meters long. So the length of pole, the entire pole is 1.95 meters. We are able to get 0.25 meters of that pole. So this section right here is 0.25 meters on one side of the fulcrum. And we're going to use another rock as a pivot point. So we're going to push down on this side to get this side to go up. The question is, ideally, how much force we're going to have to use to free our homework. And again, for ideal simple machines, finned in equals fout out. So the work we put in should be equal to the work we get out. Now the question is defining the variables. So the d in, how much is that? How much is the distance in? Well, the whole pole is 1.95 meters long. But the input side, the right side of the fulcrum, is not that long because 0.25 meters is on the other side. So the d in is only 1.70 meters. What's key here is the entire pole is 1.95, but the input side is 25 centimeters less than that because that's the side that's on the other side of the fulcrum, which means that the d out is the rest of the part of the pole, 0.25 meters. And the F out, so output is what we're going to do is we're trying to lift that thing up in the air, right? So if it's 335 kilograms, the output weight is 3,350 newtons. So the only thing left to find is ideally how much force we have to push down on to raise that side up. Now, does that mean we'd actually be able to do this? We don't know if the pole would break or bend or whatever, but what we do is ideally figure out how much force it would take, and then we do a bunch of testing, see if the pole would actually work in reality. But we're not going to do that. We're just going to figure out what F in is, ideally. So again, F in equals the F out D out. So the 3,350 newtons times the 0.25 meters, and divide that by the distance in, 1.70 meters, and that will help us find F in. So 3,350 times 0.25 divided by 1.7 means that ideally we should only have to push with 493 newtons on that pole to raise up that 335 kilogram boulder. Okay, no idea if that would actually work, but ideally that would be the case if this pole could hold. So hopefully those two problems make sense. If you have any questions, shoot me an email, let me know. And then next class we'll talk some about the review guide that you guys got, and so you have a better understanding of all of that, and we'll go from there. So thanks.